So for the source follower, we plotted our results V out versus V in, and for the experimental data, we used a V bias of 1.5 and 1.25 volts and got kappa 0.5 and 0.53. For the simulation, we got a kappa of exactly what we set the transistors to. And so the reason why we got these results for, all right, restarting, god damn it. So for the common source configuration, we have a constant current source, and our source terminal is tied to ground. So by varying the gate voltage, it'll change V out, and the gain we expect V out over V in is kappa, or negative kappa, over sigma. And we have this plotted graph here, V out over V in. And this linear region gives us a gain of 8.
Okay, so with the OTA, we have two transistors, both of which have a current through them, which is controlled by an input voltage at their gates. Both these currents have the same form that we've seen before, with the exponential, with the three different voltages which have to balance each other. So in this configuration, Vs is fixed for both of those transistors, so that's why their gains are controlled by the gate voltages. What happens when we increase V plus over V minus is the I1 increases compared to I2, which then obviously increases I out, because I out is equal to I1 minus I2. This leads to V out increasing by a factor of kappa over sigma 1 plus sigma 2, but we only see this in quite a small region either side of when V plus is roughly equal to V minus. This is because the output current has the form of a tanh function, so kind of out with this small range here, the values of the output current become constant. So with the OTA configured with the follower response, it basically has a feedback loop which should lead to it having unity gain. So that's roughly what we see. The signal's a bit noisy, but essentially this gradient of the transfer function here is 0.94, which is close to 1. Round about ground, the signal gets a bit noisy. This effect round about the ground voltage happens because V plus is kind of increasing relatively fast compared to V minus, so there's a kind of fluctuation which leads to this noisy effect before the feedback loop really kicks in and flattens it out again. So we didn't have time to properly complete the analysis on the follower integrator. Our best set of data for this circuit came at about 11:45. But what you can see is we have the step input function, and then the output voltage lags behind that slightly with the time constant slew rate kind of effect there. So if we had been trying to analyze that to calculate the slew rate, then because this output voltage has a negative exponential decay form, by subtracting it from the steady state voltage and then taking the log of that, we would have seen a linear effect with a gradient of -1 over tau, from which we could just read off the time constant. So we're only able to calculate the time constant in this way when the current has the tanh form, and the voltages are v plus and v minus are close to each other. So when v plus and v minus are roughly the same and delta v is close to 0, the tanh function essentially becomes linear with respect to delta v. So this gives a linear first order differential equation for the output voltage, which is what gives us this solution here, and which is what you see in this section of the graph here. But in this section, v plus and v minus are too far apart from each other to give that exponential result.